Good morning, class. This is Mr. Eggleston. This is Algebra 1, Lesson 5.1, using and interpreting function notation. This is just a new notation that you may or may not have seen before. If you've watched movies with math and whatnot written on the walls, usually you would have seen this notation. All right? Basically, what it is saying if you have y equals 2x plus 3, you recognize that. That's an equation of a line. We rewrite that, and we just replace y with this new, usually a lot of times it's f, parentheses x equals 2x plus 3. Notice, all I did was switch out the y to be f parentheses x. The difference between these two is this one, the one I just wrote, the one with the f, is referred to as function notation. It gives you the name of the function. In this case, f stands for function, I guess. And then it tells you what the input is. So what's inside the parentheses, in this case, x, is the input of the function. Okay? And this was supposed to be plus 3. I don't know why it didn't get transferred or got erased. And then what comes out, whatever number you get, is the output of the function. So we have the words input, usually equal to whatever x is, but we can use other letters, and output. What comes out? Okay. So we're going to do that. So understand that f of a denotes the output of a function of f corresponding to the input of a. Okay. Use function notation to describe a function's input and corresponding output. That's domain and range, words we're going to get into. And then number 3, interpret statements that use function notation in terms of a context. So that's just applying this idea of function notation. All right, so here we go. How long will it take to stop? If you've ever been in a car when the driver slams on the brakes, you know that the car does not come to a stop immediately, which is good, because if it did, we'd be dead. Because the forces on your body, if you're wearing the seatbelt, and or better yet, if you're not better yet, but or if you're not, would be so great, because if you stopped instantly, according to physics, that's an infinite force acting on your body, which would basically smush you. All right. You know that the car doesn't. Okay. So braking distance refers to the distance a vehicle will travel from the point when its brakes are fully applied to when it comes to a complete stop. What factors do you think will affect a car's braking distance? Well, think about it. There's really no correct or incorrect answer. I mean, it's just your thoughts on it. So what I would say is the make of car, specifically, how good are the brakes? Are they old? Are they mushy? And as another thought, the wear, that's supposed to be an ampersand, and the wear on the tires, and how good new are the tires, which is the only part of the car that touches the road. Again, there's really no right or wrong. Now, here's a graph of the braking distance, all right, as a function of speed. The graph shows the relationship between a car's speed and its braking distance. Some values are also given in the table. Notice, if you're not moving, then there's no braking distance because you don't have to brake. And then if you're moving at 20 miles per hour, according to this table, it says you need 19 feet to stop. 40 miles per hour, we don't know. But we do know that 60 miles per hour is 171 feet to stop, and 80 miles per hour, you need 305 feet to stop. So that's on the table. They also give you a graph that represents your speed, which is the input, which is the x value, the x thing down here. And then the output is in braking distance feet. So this is a graph of speed of your braking distance as a function of speed, which is how we would say it. All right. So if you look at this, what is the braking distance of a car driving 60 miles per hour? So let's look at our graph. Notice our graph says at 60, we go up, we're right here, and you go over, and it's kind of hard to tell from the graph, but you know what? They also gave it to you on the table. So when you're going 60 miles per hour, the table says that your stopping distance is 171 feet. So what is the braking distance of a car traveling 40 miles per hour? Notice 40 is not given to you on the table, so let's go over to the graph. And you see at 40, we're here. Okay. So it looks like we're directly halfway between 50 and 100, so it's 75 feet. How do you know? Because the graph gives the graph, which is another way of representing a function. The graph gives a value of a braking distance, a value distance, okay, of 75 feet when x equals 40 miles per hour. Okay, what does the order pair 73, 254 is on this graph? Okay, so it's on this graph. What does this point mean? So it means when the car is moving at 74 miles per hour, the braking distance you need is 254 feet. Okay. And then number 4, a car took 200 feet to come to a full stop. Estimate the speed at which the car was traveling before the brakes were applied. I should say according to this model, because this is just a model. So you want to know if you're driving, if a car took 200 feet to stop, which is, here's 200 feet. So if we just go across, okay, we're there. And if we go down, we're at the line right after 60. So there's, so the line right after 60 is 65. So every, so it goes 40, 50, 60, 70, so it's 65 feet. It will take 60, oh no, excuse me, I said feet. It's miles per hour. So the car was traveling at 65 feet, or 65 miles per hour. Sorry, I keep screwing up the X units and the Y units. All right. And then number 5, find F of 80. Notice how I said that. I said F of 80. All right, which literally means this notation. Where notice, now what was inside this before, was this the first time we used function notation? Yes. So before it was f of x, now it's f evaluated at 80. So that means we look at the graph, or actually we could just look at the table right here. When the input speed, or x if you will, is 80, it says we need 305 feet to stop, and that came from the table. Sorry, it's a habit. From the table. I do that in honor of my old buddy from Shafter High School, who we taught together for 20 plus years. All right. Then it says use function notation to express that a car traveling 45 miles per hour will require a braking distance of 96 feet. So we would say f of 80, f of 45 is equal to 96. That's the function notation. This again, this is the input. Usually it's x. This is the output. Usually y. As a matter of fact, this notation right here can also be written as an ordered pair. That would just be 45 comma 96 parentheses. It's a point. All right, so I'm trying to relate it to all the things you've seen before. All right, so here are the learning targets. Number one, functions are rules that take an input to an output. So we take this input of whatever a is, and then the mathematical words, we map it to the output. So when we put the input in, this function is going to do whatever it does, whatever mathematical things happen, and then it spits out this output, b. Okay, and f is the function name. This is evaluating a function means finding the output that corresponds with the given input. So it's like if find f evaluated at 3, or f of 3 means find output when input is 3. And the interpreting function notation must identify what the input is, key, and output represent context with proper units. All right, and that was it on the lesson portion. I'm going to do another video for the check your understanding.